Welcome students. We are studying electric charges and fields, chapter 1 of your NCERT of class 12, and we have already completed few concepts from this chapter like methods of charging a body, what do we mean by a charge, quantization of charge, conservation of charge, and in the last class we have done Coulomb's law. Now my question, before I start my today's class, I would like to ask you a question from Coulomb's law. So, do you think that Coulomb's law between two bodies gets affected because of the presence of third body? Have you understood my question? My question is that there is a force acting between two bodies. So now if I bring a third body in the vicinity of these two bodies, the force between two bodies, is it going to affect? So your answer should be no. Coulomb's law is a two-body force. So suppose if there are two bodies A and B, right? So there is a force of attraction or repulsion acting between these two bodies, right? Now if I bring another body C, then what will happen? The force which is acting on A, will it increase or decrease? So nothing as such is going to happen. The force which is acting on A due to B will always remain constant. It is not going to change because of the presence of a third or a fourth or a fifth body. So body A and B will maintain its own force between it. Okay, so if I bring body B, or suppose if I bring body C, so the force which is acting on A is because of body B and because of body C. So the total force which is acting on body A is the vector sum of both. Now if I bring another body D, then also the internal force between two bodies is never going to change. The force between body A and C will never change. Okay, but the body A will experience more force because of B, C and D. And those forces will be the vector sum, that is the net force which is acting on body A. I hope you have understood. Let us start today's class. Today we are going to study electric fields. So today's lecture is on electric field. Now when I say the word electric field, in class 12 many of you already have the idea that when we keep a charge and surrounding that charge body there is a field which is created, there is a space which is created, where if I bring another charge body, then that charge body, then the body which I am bringing, then that body will experience a force because of this body. Now before I go into depth of all these things, let me start the class with a brief introduction that why the concept of electric field was necessary. Okay. So let us consider that this is a body A, okay, and I am bringing a body B over here. Now according to me, or according to Newtonian mechanics, body B experiences a force because of body A, right? Now if I move this body B from here, from position 1 to position 2, suppose the body B comes here, then also there will be a force which is experienced, okay? Then suppose if I bring the body B here, then also the body A and B are having same force acting between them. So this forces which are acting between them is not at all changing when I am moving the positions of body B. When it is coming here or when it is coming here or at any other position surrounding the body A, when I am changing the position of body B, there is no change in force between body A and B. Even there is no direct contact between body A and B. So this force acting, which is acting at a distance, the force of or we can say action at a distance, even without any contact without contact between two bodies, cannot be explained by Newtonian mechanics. That why is it happening? Okay, now similarly we also have studied in the last class that force is inversely proportional to the square of the separation between two bodies. Now how long is this applicable? If this is body A and if this is body B, now if I keep on moving body B, if I move the body B far away from A, so will it be applicable forever or there is a limit? up to which the force will be applicable, up to which the force will be experienced by the body B. So that was also not clear from Newtonian mechanics. Now, the concept of space was not there in Newtonian mechanics. Now, Michael Faraday, he performed a very simple experiment. This experiment all of you have done in your childhood. You have taken some iron filings and you place a magnet below. What do you see? You see this kinds of appearance which takes place, right? This kinds of appearances which takes place. It's a very rough diagram. Okay, so why this kind of appearances are taking place? At that point, during the time when the concept of space was not invented and when Michael Faraday did this simple experiment, he understood by the help of this experiment that the space is always getting changed because of a force. Previously, what we have seen? We have seen that A and B, they are having force between each other. And the force is always acting immediately. The concept was very contradictory. When the body is there at B, now, when the body B is there at position 1, now when it is moving to position 2, the body A is getting the information immediately that the body B has moved to position 2 and the force between A and B is getting adjusted. But why is this happening? This was very contradictory at that point of time. So when Michael Faraday performed the experiment, he understood that the space is getting changed because of force. Right? From here, we got the concept of space, that there is space surrounding the charge. And the force which is applied by the charge, that force, they changes the space. That's why we are getting these lines of force. They are showing the lines of force. They are showing the direction of force. That means a force can change the space. And from there we got the concept space, that surrounding a charge there is a space. So how long will this be applicable? Until and unless the second body, which we are bringing in the vicinity of the source body or the first body, until and unless the second body is existing in the space of the first body, till then this is applicable. After that, the force is not applicable. The force will not be applied on the second body. Okay, now come here. Electric charges and fields. So we are studying electric field. So over here in the diagram you see there is a charge which is kept at position O. The charge is plus Q. And this plus Q charge is producing a space. It's creating a space. And this space is known as electric field. Okay, it's creating a space. Now, how to understand that there is a space which is created by this charge? I need to test it. I need to understand that is this body charged or not, or is this body has, because of this body there is a space, there is an electric field which is created. So how to understand that? To understand that, I am bringing a test charge. Suppose the test charge is Q0. So I am placing the test charge Q0 at position P. What do I get to see? I get to see that Q0 is experiencing a force. Q0 is experiencing a force because of this source charge. Okay? Or suppose I place Q0 here. So Q0 is experiencing a force here also. I place Q0 here. Q0 is experiencing a force. I place Q0 here very near to Q. So you know that force is inversely proportional to distance. So when it is kept here, more force will be experienced by Q0. When it is kept here, less force will be experienced by Q0. And if I keep it outside the space, or suppose if I have kept it here, suppose it is kept at a position X, I don't know, I cannot see electric field, it's an imaginary space. So suppose it has been kept here, right? It's not an imaginary space, this line is an imaginary line. So now when I have kept it outside the electric field, then what will I get to see? Q naught will not experience any force. Okay, therefore the electric field is not existing at point X. So to test the electric field, to test the presence of electric field, we need a test charge. See here, source charge is the charge plus Q charge is source charge which produces electric field. And test charge Q naught is the charge due to which we can understand the presence of electric field. Okay, now magnitude of test charge is always negligible compared to the source charge. So why magnitude is always negligible? We want to test the electric field, right? So if I bring a charge at position P which has a dignified magnitude, then what will happen? That charge will produce an electric field of its own. Okay, so electric field of this charge will affect this one, and electric field of this charge will affect this one. Therefore, I cannot measure only the electric field for this charge. So therefore, we take a test charge which is of very small magnitude. Hence, electric field for this test charge will be negligible. Okay. So here you see source charge, it produces electric field. Test charge, it measures electric field. So when I am keeping a test charge here, the test charge experiences the force because of the source charge. And if it experiences the force, then we can say that at that particular position, there is a existence of electric field. Okay. Now, generally when we say the word test charge, we mark it by Q naught. Q naught is generally unit positive test charge. Whenever we say the word test charge, we mean unit positive test charge. That is Q naught equals to 1 coulomb. Unit 1, unit positive test charge, it's a positive 1 coulomb. Okay, so this is the charge which we use for testing. Now over here you can ask me one question, that we have studied quantization of charge, and there we have got to see that the minimum charge of an electron is 1.6. The charge of an electron is 1.6 into 10 to the power minus 19 coulomb, and that is the minimum amount of charge which can exist in a body, right? So this is 1 coulomb. So it's contradictory. So in that case, I will tell you, generally whatever bodies we consider or whatever bodies we have in our real life, those are not point charge. They have some dimensions. Suppose if I take a book, okay, or if I take this page. So this page have some dimension, right? So obviously, if I want to measure electric field because of the presence of a source charge, so that source charge will have some dimension. Compared to that source charge, the unit positive test charge which we take are always very small. So what is electric field? Electric field is the space around any electric charge in which its influences can be felt, so that any other charge in that region is acted upon by a force is known as electric field of that charge. That means it's a space around an electric charge. As you can see in the previous diagram, this is a space around an electric charge where you bring the another charge. Suppose you bring another charge Q over here, this Q will experience a force because of, suppose this is Q dash. So this Q dash will experience a force because of this source charge. Okay, and this space is known as electric field. Now if I say the word electric field intensity, the word electric field intensity means how strong is the electric field. If the electric field is very strong, then more force will be applied on the test charge, and if electric field is less strong, then less force will be applied. Okay, so electric field intensity measures how strong, the strength of an electric field. See, the intensity or strength of an electric field at any point in that field is the force experienced by a unit positive charge placed at that point. Okay, so when we are placing a unit positive charge in an electric field, then whatever charge is experienced by that unit positive charge, because unit positive charge, they have no capacity to produce their own electric field. So they will experience force only because of the source charge. So whatever force they will experience, that amount of force is equal to the strength of the electric field, the electric field intensity. So generally we have studied about two terms right now, electric field and electric field intensity. Both of these things are denoted by the symbol E, and E is a vector quantity. Why? As you all know, electric field or intensity of electric field is because of the force which is experienced by the charge, unit positive test charge. So force is a vector quantity, and hence electric field will also be a vector quantity. Now suppose if I talk for this two body, for this one body, for this body and for this body. So suppose this is a point charge. So what will happen? There is a space created. So this positive charge will keep on, there is a electric field lines, we will study about it. So suppose this is the direction of electric field. Okay, the electric field lines, they are getting diverged throughout the space from this single point. Okay, so if this is the direction of electric field, then what will be, suppose there is the charge Q0. Then what will be the direction of the force? This will be the direction of force which is applied on Q0. That means direction of electric field and direction of force, they are always acting on the same direction. Okay, E is equals to F if we are taking a charge of 1 coulomb. So what we got to see, that electric field intensity E vector is the force experienced by a unit positive test charge, or we can say force per unit positive test charge. So E equals to F by Q0, the force experienced by a unit positive test charge. So if we say Q0 equals to 1 coulomb, then electric field equals to the force. If I put Q0 over here, if I put 1 coulomb, it will be E equals to F vector. And you can see there is no negative. That means both electric field and force, they are along the same direction. Okay. So how can you measure electric field for any charge? So suppose there is a electric field, and that electric field is 10 Newton per coulomb. Unit for force is Newton. Unit for charge is coulomb, right? Now if I bring a source charge, test charge. So test charge is how much? 1 coulomb, right? That is E equals to F. So the force which will be experienced by the test charge will be 10 Newton. Okay. So this is, or if I say that a force, suppose I brought a test charge. Okay, I brought a test charge Q0 equals to 1 coulomb. Clear? I need to find out the electric field. Now, I measure how much force is acting on that test charge. I got to see that force acting on the test charge is 10 Newton. Therefore, I can say electric field is 10 Newton per coulomb according to this formula. E equals to F by Q0. The force which is experienced by the charge is 10 Newton. Charge is 1 coulomb. So electric field will be 10 Newton per coulomb. So I can measure electric field in this way, or I can measure force acting on the charge. Okay. What is the unit? Unit is Newton per coulomb. There is another unit, that is volt meter inverse. Okay. How will I get this unit? See, Newton per coulomb. If I multiply both up and down with meter, Newton into meter, we have studied walk. Walk is force into displacement. What is the unit of walk? Joule. Joule, coulomb into meter. Right? Now we have studied potential. V equals to W by Q. Right? Okay. So W is joule, Q is coulomb. joule by coulomb equals to volt, potential difference unit, volt by meter, that can be written as volt meter inverse. Clear? Now I will calculate the dimension for it. So let me calculate the dimension in this paper. Now I am going to calculate the dimension. Now we know E equals to F by Q naught, right? What is the dimension for force? All of us, we know it, ml t to the power minus 2, right? Q naught, we know current is I equals to Q by T, so Q equals to IT. What are the dimensions? What are the dimensions? Ampere time, so ampere time, so that will be ml t to the power minus 3 a to the power minus 1. Be careful, you always need to give the third bracket for writing the dimension. And the dimension for electrical properties are very important for your exam, for 1 marks questions. Okay. Now we are going to find electric field due to a point charge. How much is the electric field which is acting for a point charge? So here I am taking an xy plane, okay, xy plane, and at the origin of xy plane I am keeping a charge q, right? Now I need to measure electric field for this charge q. So what will I do? I will bring a test charge. So I have done so. I have brought a test charge, and the separation of the test charge from the source charge is r, right? Now according to Coulomb's law, I know that this test charge will experience a force because of this source charge. Now test charge is of very small magnitude, hence negligible force applied on Q, hence negligible electric field. So the force which is experienced by Q naught due to Q is F, which is equals to 1 by 4 pi epsilon naught according to Coulomb's law, Q naught by r square. Now we have studied E equals to F by Q naught, right? So therefore we can write F equals to EQ naught. This is the force which is experienced by the test charge, okay? So here I got F, here I got F. I can equate both equation 1 and 2. So 1 by 4 pi epsilon naught Q naught by r square equals to E Q naught. Q naught and Q naught get cancelled out from both the sides. So what am I getting? E equals to 1 by 4 pi epsilon naught Q by r square. If I want to write this in vector form, I will bring a vector sign. Vector needs a direction, unit vector r cap, okay? So this is electric field with respect to source charge. See, this is electric field because of the big charge, source charge, right? And this formula is electric field because of or with respect of test charge. Okay, so this is electric field with respect to test charge. This is electric field with respect to source charge. Now next is electric field lines or electric lines of force. Now we already know that electric lines of force or electric field, it is a vector quantity, okay? So if it is a vector quantity, definitely it should have a direction. So how to find out the direction? There is a space, but we cannot see that space, okay? It's an imaginary space. So how to understand that electric field, what is the direction of the electric fields? So to understand the direction of electric field, we have assumed a concept that is electric field lines, and that is imaginary lines which is used to understand the direction of electric field. With help of electric lines of force, we can understand what is the direction of electric field. So let us see the definition. Electric field line is an imaginary line or curves. It can be a line, it can be a curve. Okay, as you have seen in the experiment of magnetism, the lines of force, they were curved lines. Okay, the tangent to which at any point gives the direction of the electric field intensity. So it can be a straight line, it can be a curved line. I cannot draw a tangent on a straight line, but if I draw tangent on the curved line, then that tangent will represent the direction of the electric field intensity. So let us understand this. Suppose I have taken an isolated positive charge. Okay. In case of isolated positive charge, electric field intensity is always outwardly directed. It always comes out from the positive charge. Okay. We assume, for an ideal case, we assume that line starts from positive charge and it can diverge up to infinity. The line keeps on diverging and hence it creates a space, a circular space surrounding the charge. So why the electric field lines? They are directed outward. So to test electric field, we always need a unit positive test charge. So suppose if I bring a unit positive test charge, that is plus Q naught, this plus Q naught and this positive charge, they will have a force of repulsion between them. That means this plus Q naught, if I keep plus Q naught over here, if I bring it very close here, if I bring it here, plus Q naught, what will happen? This plus Q naught will suffer a force of repulsion. That means this plus Q naught will move away. Okay. So if it is moving away, it is showing the direction of the electric field intensity. Similarly, for an isolated negative charge, it is inwardly directed, and in ideal case, we assume that lines comes from infinity and it converge on the charge. It comes from infinity and it converge. All the charges, they converge at this point. So why this is happening? Suppose now if I bring a charge Q naught plus Q naught over here, a unit positive test charge. So this plus Q naught will be attracted towards minus Q. That means this plus Q naught will move towards the negative charge. If I keep it here, it will move towards the negative charge. Okay, and hence we can say that the plus Q naught is showing the direction of the electric field. So here we can say one thing. If it's a case of an isolated positive charge or if it's a case of an isolated negative charge, the direction of the unit positive test charge is showing us the direction of the electric field intensity. If I keep a unit positive test charge, the test charge will move in this direction. The test charge will move away from the isolated positive charge and hence it will show the direction. Or if I keep a positive test charge here, the positive test charge will come in this direction. It will come near to the isolated negative charge and hence the movement of unit positive test charge, the direction of the movement of the unit positive test charge determines the direction of electric field. Okay. From this two diagram, you can understand another concept. See, we can say that electric field lines, they emerges out from positive charge. See, they are moving out from a positive charge. Whereas electric field lines, they enters into a negative charge. Okay. So electric field lines emerges out from positive charge and enters into negative charge. What we can see from the diagram. Direction of positive test charge determines the direction of electric field. So if I need to understand the direction of electric field for a system, what will I do? I will place a unit positive test charge there and I will see the direction. So if I can observe the direction, if I can understand the direction in which it is moving, I can understand the direction of electric field. So with the help of test charge, I can understand how much is the magnitude of electric field intensity and what is the direction of electric field intensity. Okay. here we have taken two equal charges, plus and minus, but they are equal in magnitude but they are opposite charges. And as you all know, this type of a thing which we get to see if there are two opposite charges. Why? Suppose if this is the positive charge, I am drawing it here also separately. If this is a positive charge Q and here I have a negative charge minus Q, right? And if I bring a test charge here, the test charge will do what? The test charge will suffer a repulsion from plus Q, whereas the test charge will suffer an attraction for minus Q. Therefore, this plus Q, due to plus Q, it will move away, and due to minus Q, it will try to come near towards minus Q. Okay, this is what is happening here in this diagram. If I leave a test charge, unit positive test charge here, Q naught, this Q naught, due to repulsion, it will move away from here. And there is a force of attraction which is acting due to this. This minus Q is pulling Q naught towards it. So this Q naught, because of the force of attraction, it will go near to minus Q. So we said that we can determine the direction by placing a test charge in the electric field. See, the test charge will move in this way from here to here, from here to here. It will determine the direction, right? It will determine the direction. How will it determine the direction? If see, I have drawn separately two electric field lines over here. So suppose if this is position P, there are two charges equal and opposite, okay, equal in magnitude but they are opposite in polarities. Now if I choose point P and if I place a test charge Q naught at point P, then what will happen? For this positive charge, the test charge will experience a force. Let us name this E1 vector, right? And for this minus charge, again the test charge will experience a force, and that will be somewhat in this direction, E2 vector, right? If I place a test charge Q naught at P, the test charge will experience an electric field because of this positive charge which will be directed here, okay, repulsion, and this negative charge is pulling the test charge towards it. So because of my electric field, because of the negative charge, the test charge will be pulled in this direction. Okay, so what will be the net direction for this E1 vector and E2 vector? So that is the resultant of E1 and E2 vector. So if I draw a tangent, the resultant of E1 and E2 vector is the tangent to the surface. At every point it will be a tangent to the surface, right? It will be a tangent to the surface. So the tangent which is drawn on the surface, that is showing the resultant electric field. Clear? Now the intensity of the electric field E1 will be much more than the intensity of electric field E2. Why? Because E1, this charge, if I place the charge over here, this position P is near to E, near to plus positive charge. That means this distance is less, electric field will be more. Whereas in this case, what is happening? The distance is more. Over here the distance was less, electric field was more. But here the distance is more and electric field will be less, because electric field is inversely proportional to the square of the distance. Now we will come to the properties of the electric lines of force. So field line starts from positive charge and ends into negative charge. Tangent on the electric field lines shows the direction. Density of lines of force determines the strength of electric field. Yes. Here in the diagram, if you see this diagram, over here the electric field lines, they are highly near to each other. They are very near to each other. So if they are very near to each other, here they will have a strong electric field. And if density of electric field lines, they decreases as we move far, the density will keep on decreasing, right? And if density of electric field lines decreases, then the electric field becomes weaker. suppose if I draw a diagram over here, and if I place a cross section, right? So here the electric field lines, they are very close to each other, and more number of electric field lines, they are crossing through this particular cross section, right? So electric field at this place will be very strong, whereas less number of electric field lines are passing. The electric field lines, you see, they are spaced, they are not that dense like this one. So electric field at this position will be weak. Two electric lines of force can never intersect. Yes, if this is an electric field line, the tangent drawn on this electric field line will show the direction. If this is an electric field line, they have intersected, the tangent to this one will show the direction. So if two electric field lines are intersecting, what is happening? This tangent is showing direction in this direction, this tangent is showing direction in the other place. This is E1, this is E2 for a particular point P. So is this is possible that for a particular point P you are getting two directions of electric field? No, it is not possible. Therefore two electric field lines can never intersect. Now we are coming to numericals, and this is a very conceptual numerical. Over here you can see 50 centimeter, there is a separation between 2 points A and B. A charge of plus 20 ESU, electrostatic unit, is kept at A, and plus 80 ESU is kept at B in vacuum. Okay, so ESU means CGS unit, 1 by 4 pi epsilon naught in free space, that is in vacuum or air, K equals to small k equals to 1. Where will be the electric field 0 on the line joining the two charges? That means a line which is joining these two charges, I need to find out the position on this line. Okay, I need to find out the position on this line where the electric field will be 0. That means I need to find out the null point on that line. The null point means where electric field becomes 0. So this is the case. See, plus 20 ESU, plus 80 ESU. That means both the charges are like charges. Okay, I have drawn the diagram here. I have kept 20 ESU and 80 ESU. This is my formula to be used because I need to find out electric field, E equals to KQ by R square. Achha. Now I need to understand first that electric field, the point where the electric field will be 0, will that electric field point will be on this line, will be between A and B, or will it be outside A, or will it be outside B? Will it be on this side? Will it be on this side? Or will it be between A and B? How can I understand that? We know for a positive charge, what happens? The electric lines of force, they move outside, right? And for a negative charge, the electric lines of force, they move inside. Now, if I want to make electric field 0, that means they should be equal in magnitude but opposite in direction, right? Suppose this is two electric field E and E, they're equal in magnitude but they're opposite in direction. Or this can be the condition, right? So I need this type of a condition. Okay, so here suppose if I place a test charge, or if I consider a point P over here, you see, if I place a test charge over here, the test charge will suffer a repulsion. Okay, from positive test charge, electric lines of force, they are moving outward. From this also electric lines of force are moving outward. So is it satisfying this or this condition? Yes, it is satisfying the condition. That means electric lines of force will be somewhere in between A and B. So let us consider, let me take that X is the position from A where electric field line is 0. Now you can ask me, you can take it here also mathematically, but you can ask me that why I am taking it near to the smaller charge. See, I need to make it equal in magnitude as well, right? So suppose if I say, how can you make 3 equals to 5? So what will be your answer? You need to add two numbers, right? Two numbers with the smaller number. Then only you can make it equal to 5. So if I take the charge, if I place the position here, then what will happen? Distance of this position from A will increase. Therefore, electric field for A will decrease far. But if I take it here, what is happening? The distance of this point from A is less. Therefore, electric field for this particular position will increase. Okay? So, if I place a charge over here, I can understand that I am going to get a null point at the center at somewhere between A and B. So this is my formula to be used. Okay, K equals to 1 for CGS unit. 20, what is the distance? X square equals to 80 divided by, it's 50 centimeter. So I can write 50 minus x square. Okay, so if I solve it, 0 and 0 will cancel out. This will become 4. So I can write 1 by x after square root and everything. 2 by 50 minus x, or 50 minus x equals to 2x, or 3x equals to 50, or x equals to 50 by 3, which will come near to 16.66 something centimeter. So that means at a position of 16.6 centimeter between A and B, at that position electric field will be 0. Okay. Now this is the case where I have considered both the charges of same polarity, like charge. Now if I consider one charge is positive and the another charge is negative. Suppose if I take it here, one charge is positive, 80 microcoulomb, another charge is, was it 80 microcoulomb? Yes, another charge is negative, minus 20 microcoulomb. Okay, or I can take it at ESU as before, ESU, and the distance between them is 50 centimeter. Right, this is positive, this is negative. Now where will be the electric field line 0 at which position? So what is my condition? This is plus, this is minus. So from plus electric field lines will come outside, from minus electric field lines will enter into a negative charge. So is this condition satisfying? No. If I place it here, suppose if I place the test charge here, then what will happen? Electric field lines from plus, it is moving outward. Okay, and it here, let me see, if I place it here also, if I take this position, then also minus it is entering, and from plus it will move outside, right? Plus Q naught, it is moving outside. So this condition is also satisfied. This is also the condition which is satisfying. Which one to take? See, they should be equal in magnitude as well. Now 80 ESU is a big charge, and if I place the test charge, or if I take the point which is near to 80 ESU, that means if separation is less, electric field will be more strong. So this is already a strong charge producing a strong electric field, and due to less distance the electric field will be much stronger. So I cannot choose this position. Which position I can choose? I can choose this position where what is happening? This is a weak charge, right? And if I decrease the distance for this one, electric field will enhance for this charge, and hence they will be equal in magnitude and opposite in direction. So this one is applicable. So let me take this distance. When you will be drawing it in your examination copy, it should look very clean and clear, and the diagrams should be drawn with pencil. let me take the distance x. You should not draw in this way. It should be very clean diagram with pencil. Okay, the distance should be x. So for this one, how much is the electric field? 20, right? X square. And for this one, it is becoming 80. 50 plus x. 50 plus x whole square. You will solve and you will find out x. I hope you can do it. Okay, you can solve and you can find out the value of x, and at that particular position the value for electric field will be less. So if I solve it, let me solve it only. What will I get? 1 by x into 2, 50 plus x. So 50 plus x into 2x. So I am getting 50 equals to x, or so I am getting x equals to 50. That is means from this charge, from point B, if I mark, from point B it is 50 centimeter away. That means from point A it is 100 centimeter away. The point where the electric field will be 0, for point A it is 100 centimeter away from point A, and for point B it is 50 centimeter away. So from point A, it is 50 plus 50, 100 centimeter away the point locates, which is known as null point for the above drawn system. Okay, next come to here in this diagram. Now this kind of a diagram you have done for Coulomb's law as well. See, you have a box, plus q plus q plus q charge are kept at 4 corners. You need to find out electric field at the center. Okay, so if you place a positive charge here, right, what will happen? And suppose if I take it here, what is happening? This q, okay, it will produce an electric field in this direction. This positive charge q will produce an electric field in this direction. This q will produce an electric field in this direction. This q will produce an electric field in this direction. So they are all cancelling out in each other. As for Coulomb's law also, we have seen that the forces, they got cancelled out. Okay, this one cancelling this one cancelling this one. Hence, the total electric field at the center will be 0, right? For this particular diagram, again same thing, electric field at the center, right? So for plus q, this is the direction. For minus q, what happens in minus q? It moves towards minus charge, right? For plus q, if I bring a test charge here, it will move here. For plus q, okay, sorry, for plus q it will move outward. For this one, move outward. So this one and this one, they are cancelling out each other. Hope you can see this one and this one, they are cancelling out each other. Whereas this one and this one, they are in the same direction. So the resultant electric field at the center will be electric field for plus q charge and electric field for minus q charge. You can find it out on your own. Find it out. Okay. Now here in this diagram you can see that there is a pendulum bob which weighs 80 milligram. Right? Now there is a charge, there is a pendulum bob which has a charge of 2 into 10 to the power minus 8 coulomb. The bob rests in a horizontal, okay, with this amount of charge, and the bob rests in the horizontal with the electric field of 20 kilovolt meter inverse. You need to find out the tension and you need to find out the angle of the string with vertical. That means this angle of the string with vertical you need to calculate. You need to calculate theta. So here this is the tension of the string, right? This tension of the string can be resolved into two components, right? It's a tensional force, vector quantity. So it will be theta, it is making an angle theta. So there it's making an angle theta, that will be t cos theta, and this one will be t sin theta. Okay, there is a mg force which is acting downwards, and there is an electric field which is acting on the charge, due to which it is moving in a direction. So the force which is acting horizontally because of the electric field is 20 kilovolt meter inverse. So the force which is acting is QE, right? So we can say T sin theta equals to QE and T cos theta equals to mg. I need to find out theta. Dividing both equations, I get, this is equation 1, this is 2. Dividing 1 and 2, I get tan theta equals to QE by mg. Put the values. Okay. Let me take this as big Q as it is given in the question paper. Okay. So what is Q? 2 into 10 to the power minus 8 coulomb. We will put the values. 20 into kilovolt meter inverse. So you need to do the conversions properly. 20 into 10 to the power 3 volt meter inverse. 80 milligram need to be converted into kg. 80 into 10 to the power minus 6. You will put all the values and you will find out the theta. And how will you find out tension? Put the value of theta in any of the equation. Put in this equation. T cos whatever value will come, put it here. Mg, put the values and find out tension. You are supposed to get this answer. So if you get this answer, tell me, comment me down in the section below. Next day we will start with charge distribution. For today this much is your class. Thank you.